This video is an introduction to proofs with segments and angles. In geometry, we don't assume something to be true just because it looks like it might be true. We prove it in a logical, step-by-step manner using reasons that we already know to be true. These reasons are often theorems, postulates, definitions, and properties. Let's take a look at a couple examples here. So our first example is a segment proof. And this says, prove that if the length of segment AB is equal to the length of segment CD, then the length of segment AC is equal to the length of segment BD. And here we have a diagram showing us that. So we know that AB is congruent to CD, and we need to show that this segment here, AC, is the same length as this segment here, BD. Now you might look at that and go, well, yeah, it's obvious, but we actually have to prove it step by step. First thing we want to do is state what is our given information, and that's usually what follows the word if. So it is given that the length of AB is equal to the length of CD. And then what we have to prove is what's stated after the word then, that AC is equal to BD. And you'll see here that I have a little table with one column that says statements and one column that says reasons. This is what's generally called a two-column proof. There are other ways to write proofs. You can also do a paragraph proof, which is just sentences, or a flow proof, which kind of uses arrows that points to different things. I'm just going to show you a two-column proof here. So our first statement is always the given information. So I know that AB, the length of AB, is equal to the length of CD, and I know that to be true because that is what is given. Now I'm going to take a look at this and say, well, I don't really care about AB and CD. What I'm more interested in is AC and BD. Notice that if I take this first equation that I have here, AB equals CD, I can add BC to each side. So AB plus BC equals BC plus CD. So all I did was took my original equation in statement number 1 and added the length of BC to each side. This is called the addition property. And this is what you've used in algebra, where you can like add 5 to both sides of an equation or subtract 5 from both sides of an equation. Okay, so now I have that statement. Now looking at my diagram, I can see that AB plus BC equals AC, and BC plus CD equals BD. So I'm going to say that. AB plus BC equals AC, and BC plus CD equals BD. And this is something that's called segment addition postulate. Segment addition postulate. Segment addition postulate says that if I have two smaller segments that are right next to each other, when I add their lengths together, it's the same as the length of the larger statement. At the end of this video, I'll go over that in more detail with you. So notice that I have AB plus BC equals AC, BC plus CD equals BD. I have one more step to do because up above I said that this was equal to this. Well, AB plus BC is AC, and BC plus CD is equal to BD, and I know that those two are equal to each other. And the reason that I could do that is by substitution. I knew that these two statements here were equal to each other, so I can substitute and say that these two are equal to each other. And there we're finished with that proof. Let's take a look at a second one here that deals with angles. Oops. And this one says, prove that if angle ABE and angle DBC are right angles, then the measure of angle ABD is equal to the measure of angle EBC. So let's take a look at the picture here. So angle ABE, that's a right angle, and angle DBC, that's a right angle. And what I'm trying to show is that angle ABD, so that would be this one right here, is equal to the measure of EBC, that would be this one right here. Now again, you're probably looking at this and going, well, of course, that's obvious. You would just kind of take this middle angle here away from both of them. And that's great, but we actually have to say that step by step. So let's go ahead and fill in our proof here. So we are given that angle ABE and angle DBC are right angles, and we have to prove that the measure of angle ABD is equal to the measure of angle EBC. Okay, so my first statement again is going to be my given information. ABE and angle DBC are right angles, and I'm going to abbreviate here so I can fit that in there. And my first reason is given. Now, one thing I know is that since they are both right angles, they're actually going to be equal to each other. So I know that the measure of angle ABE is equal to the measure of angle DBC because all right angles are congruent. So I know that those two angles are equal to each other. Okay. Oops. Now I'm going to use a little angle addition postulate and say that notice that angle ABE is equal to these two smaller angles right next to each other. So the measure of angle ABE is equal to the measure of angle ABD plus the measure of angle DBE. And then looking at the other one, the measure of angle DBC is equal to the measure of angle DBE plus the measure of angle EBC. Very similar to what we did with the segments when the two smaller segments added up to the larger segment. Now I'm taking a larger angle and saying that that adds up to the two smaller angles that are right next to each other. And as we had segment addition postulate, this is going to be angle addition postulate. And at the end of this video I'll have a chart describing that, a diagram of that. Okay, so I know that ABE is these two angles, and I know that DBC is these two angles, and I know that ABE and DBC are equal to each other, so I can just say that these two statements here are equal to each other. So the measure of angle ABD, so I'm writing this part right here, plus the measure of angle DBE, DBE is equal to the measure of angle DBE plus the measure of angle EBC, and I'm running out of my box here. Okay, so these two parts here are equal to each other, and the reason that I can say that is by substitution, because instead of writing ABE and DBC, I wrote the two angles that they were equal to. Now notice that in this statement here, sorry it's a little sloppy, I have a DBE on each side. So similar to the first proof where I added something to both sides, here I can subtract something from both sides. And when I do that, I have that the measure of angle ABD is equal to the measure of angle EBC. And the reason I can do that is the subtraction property. Be careful when you're abbreviating substitution and subtraction. Okay, and as you can see, I've gotten to what I was supposed to be at. So once you've worked your statements and reasons through and you get to what you need to prove, you're basically done. So that's what an angle proof looks like. So how do I know what to use? Really, you should have kind of a toolbox of all sorts of properties, theorems, postulates, and definitions. These are going to be the reasons that you use in your proof. Let me go over two that I used up above. And the first one was segment addition postulate. And that says that if points A, B, and C are collinear, and if B is a point that's between points A and C, then the length of AB plus the length of BC equals the length of AC. And here's a diagram here. So this length of AB plus the length of BC, and notice those points are collinear, is equal to the length of the larger segment AC. Angle addition postulate is very similar. It says that if D is a point in the interior of the large angle ABC, you can see that D is a point in the interior, then the two smaller angles that make up that large angle, the measures of those two make up the measure of the large angle. So the measure of angle ABD, which is marked here in red, and the measure of angle DBC, marked here in blue, is equal to the measure of the large angle. I would also like you to refer to the definitions of the terms that you saw in the vocabulary exploration activity in topic 1. You can reference my previous video on naming and constructing lines, angles, segments, and rays for that. Also, here are some properties of real numbers which apply to segments and angles as well. We saw the addition property where you can add the same thing to both sides of an equation. There's also the subtraction property. We saw that as well, where you can subtract the same thing from both sides of the equation. Multiplication and division, those don't come up quite as much in geometric proofs, but they can. Sometimes we need to say that something is equal to itself. That's called the reflexive property. Sometimes we need to flip something around on either side of the equal sign. That's called the symmetric property. The transitive property, this is kind of a cool one. It says that if A is equal to B and B is equal to C, then A is equal to C. Kind of like substitution, which leads us to the substitution property that says that if A and B are two things that are equal, then I can replace A with B or B with C in any equation. And then you're probably familiar with the distributive property, less visible in geometric proofs. So this video took a look at an example of a traditional two-column proof that uses segments and one that uses angles, how we create a column for reasons, column for statements, a column for reasons, and then we went over what some of the reasons that you might be using in these proofs are.